Today we'll be talking about a new feature introduced in OpendTect 7.03 that gives you access to the data in your OpendTect surveys from Python called the odbind Python module. The plan for this webinar is to start by providing some background on OpendTect and Python, and then an overview of the odbind Python module itself, its current status, what you need to use it and how to get started, as well as some information about the structure of the Python API. After that, I'll present a short Jupyter Notebook demo to show some examples of what is possible, and then finish up by describing our future plans for the module. OpendTect and Python have a rich association. For some time, the OpendTect software installer has shipped with curated Python Conda environments for general numerical computation as well as more specialized applications like machine learning. Also, the OpendTect UI provides tools to select the active Python environment and icons to launch Python IDEs like JupyterLab, Spider, or Visual Studio Code. From a Python developer's perspective, OpendTect also provides a number of options to work with project data. There's the ODPy open source module developed by DGB Earth Sciences, which provides limited access to some OpendTect data types, but architecture limits its practical use to small things like well data. Access to heavier data like seismic or 3D horizons is generally not feasible. There's also the DGB open source module, also from DGB, that mainly exists to support their commercial OpendTect plugins such as machine learning. odbind is another DGB project which developed an experimental direct Python binding to the OpendTect C++ API using the PyBind 11 tool. It provides fast direct access to data using the OpendTect C++ code, removing some of the limitations of the ODPy architecture. However, a major drawback is a requirement to build a separate binary package for different Python versions. There is also WMPy, which is part of my open source WM plugin suite. It is a collection of Python scripts for calculating seismic attributes using the OpendTect attribute engine and my external attribute plugin. And finally, the new entry, which is odbind, which is the subject of this webinar. It is an open source Python module and associated C++ code packaged as an OpendTect plugin. Like odbind, it provides fast direct access to data using the OpendTect C++ code. It is simpler to build, package, and use as a single plugin binary is compatible with all recent Python versions after and including 3.7. Introduced in OpendTect 7.03, the odbind Python module and plugin provides a Python API for working with data stored inside OpendTect projects. It uses the C-types Python module to bind to the OpendTect software libraries and is currently packaged as a plugin within the OpendTect code repository. Key features include fast direct access to project data from Python. You don't actually need to run OpendTect to use the module. You just need to make sure that the bin Python folder of your software installation is on the Python path. You can access multiple surveys in a single session. You have easy access to object metadata. You have easy access to large data like seismic and horizons. Where possible, we want to support advanced Python data types like pandas data frames, X-array data arrays, and datasets. To the right is an example of using the integration between X-array and matplotlib to display an horizon structure map. Memory for large data is allocated and managed by the Python interpreter. Also, a single plugin binary is compatible with all recent versions of Python. The odbind Python API currently consists of 9 classes that map to the corresponding underlying data types managed by OpendTect. As of 7.03, read-write access from Python has been implemented for 4 of these data types: wells, 2D line geometries, 3D seismic horizons, and 3D seismic data. For the rest, only read access is available in the current release. The main requirement is that you have OpendTect 7.03 or later installed. Either the free or pro versions is okay. You also need a Python environment. The good news is that any of the Python environments available through the OpendTect installer will do. If you prefer to bring your own Python environment, I've listed the packages we'd recommend installing. A key requirement is that the bin Python folder of the OpendTect software application must be on the Python path before importing odbind. So here is a summary of what you need to do to use odbind. In particular, there are 3 ways to use the module as a Python programmer. Firstly, you can run your code in a console window or IDE session launched from the OpendTect UI. In this case, OpendTect will set the Python path automatically. In the demo, that's how I will start a Jupyter Lab session. The second option is to add the bin Python folder of the OpendTect installation to the Python path environment variable before running your scripts. Thirdly, add the lines shown here to set the Python path at the top of the script before the odbind imports. Note that the last 2 options don't require you to actually run OpendTect at all. Our aim is to have an easy-to-use API which is consistent as possible across all classes. We also want to take advantage of advanced Python types like data frames and arrays where that makes sense. While the API is still a little bit fluid, these are some of the details. All odbind classes have a common set of functions to extract information of interest. The names function returns a list with the names of the related OpendTect objects. This could be all surveys or all 3D seismic volumes. The infos function returns a dictionary with basic metadata for the objects. The infos data frame returns the same information, but this time in a pandas data frame format. Features returns a GeoJSON feature collection with a GIS representation for the objects. In the case of the survey object, the method arguments are the base data folder, and for the last 3 methods, a list of surveys to include. If neither is provided, then the current user's last base data folder and all surveys is the context. In the case of the data objects, things like wells, seismic 3D, etc., the method arguments are a survey object and an optional list of object names to include. The survey class in each of the data object classes has a constructor used to create read-only instances of the class. The survey class constructor takes a name and optionally a base data folder as arguments. The data object classes take a survey object and the object name as arguments. Data classes that support writing also have a create method that makes and names a new object. Exact set of arguments depends on the object type. However, the last argument is always a Boolean flag called overwrite, which determines what happens if an object of the given name already exists. The default value of overwrite is false. Finally, there are 2 functions provided to query the current user's OpendTect settings for the base data folder and the last used OpendTect survey. Let's proceed to the demo. I'm using Linux, OpendTect Free 7.03, and the Miniconda 3 Python environment delivered by the OpendTect installer. For the demo, I'm starting a Jupyter Lab session from the OpendTect UI. As mentioned, you can always set the Python path manually and run your code without actually starting OpendTect. By starting from the UI, the Python path is automatically set based on the software installation, as you can see here. After importing the odbind module, the getUserData directory and getUserSurvey functions are available to query the current user's OpendTect settings. The survey names function provides a list of survey names. By default, the current user's base data folder location is used. Surveys in other locations can be queried by specifying the appropriate base data folder. The survey infos data frame function gets a pandas data frame with basic metadata for the surveys in either a given base data folder if provided, or in the user's current base data folder. Note the use of lists to limit the scope of the query. In general, this function will most likely be used with no arguments to receive information for all surveys in the current user's base data folder. The survey features function returns a GeoJSON rectangle object showing the geographic extents of the surveys in the query. This can be displayed using a web mapping widget like Folium, which is used here. It is also possible to program the contents of the pop-up that appears when the GIS objects on the map are clicked. The GeoJSON contains all the metadata provided by the info function. In this demo, I just show the survey name. The survey class also includes methods to convert from inline crossline to easting northing coordinates. To use the Seismic 3D class, I first have to create a survey instance, here one of the F3 demo projects. The Seismic 3D names function gives a list of the 3D seismic volumes in the specified survey, and the Seismic 3D infos data frame function gives a pandas data frame of metadata. The Seismic 3D features method returns a GeoJSON collection of the rectangular extents of the surveys in the query. Note the use of lists for both functions to control the scope of the query. To access actual seismic data, I first have to create a Seismic 3D instance, in this case for the dip-steered median filter dataset of the F3 demo project. The ranges property provides a summary of the inline, crossline and Z range of the dataset. The Seismic 3D API for accessing seismic data is similar to that used by Equinor's SegWay.io Python module. To get inlines, I just use the iLine member object of the Seismic 3D instance. Indexing this object with a valid inline number returns a tuple with a list of NumPy arrays of seismic data, one for each component, and a dictionary with metadata for the inline, such as component names, crossline numbers, coordinates, etc. The class includes a function to convert these data types into Xarray datasets. The full functionality of Xarray can then be used with the data. Here I produce a nicely labeled plot of the selected inline. In the next release of odbind, indexing the iLine object will directly return an Xarray dataset by default. Also, the CDPX and CDPY coordinate names will be shortened to just X and Y. I can get a specific crossline by indexing the Xline attribute of the Seismic 3D object with a valid crossline number. It is also possible to index a regular sampling of a range by using a Python slice object. A Python slice is three numbers, the start, stop, and step of the range, punctuated by colons. The start and stop must be valid crossline numbers. Python convention is for the range of indices not to include the stop index. However, to be consistent with how OpendTect interprets ranges, the crossline indexing includes the stop index. So in this example, 400, 600, 100 results in crosslines 400, 500, and 600. Note that slice indexing can be used to index inlines and Z slices as well. Also, slice indexing produces a Python generator object and not the data itself. You have to iterate over this generator to access the actual data. This is called lazy evaluation. Here I access and display three crosslines using a for loop. To access Z slices, you use the Z slice attribute of the Seismic 3D instance. Indexing is based on Z sample number in the volume. 0 is the index of the first sample. This is not necessarily a time or depth of 0. The Seismic 3D instance has a method zIndex for converting an actual time or depth to the nearest Z sample index. I use it here to get the index of the Z slice at 1600 milliseconds in this particular data set. There is also a zValue method for conversion in the opposite direction. It is also possible to access individual traces using the trace attribute. Traces can be indexed by trace number within the volume, where index 0 is the first trace in the volume, -1 or trace count -1 the last. Here I'm reading and plotting trace number 200, the 201st trace of the seismic dataset. The Seismic 3D instance has methods for converting between trace number and inline crossline coordinates. Here you can see trace number 200 corresponds to inline 100 and crossline 500. Traces can also be indexed by actual inline crossline number pairs. It's not shown here, but both types of indexing can also use Python slice objects. Indexing using Python slices produces a Python generator that, when iterated, will return a trace at a time from the indexed range. Note that when using slices for indexing and crossline indexing, that the order of traces delivered by the generator has the crosslines as the fast index. The volume attribute of the Seismic 3D instance reads a 3D subvolume into memory. Indexing requires three elements. The first two are Python slice objects specifying the inline and crossline extent. The third element can either be a Python slice object specifying the Z sample index extent or a Python list with the Z value range, that is, the start, stop, and step time or depth. You can see some examples of subvolume indexing here. Especially note the use of a lone colon as shorthand for the entire data range of a particular coordinate. In the notebook, I'm reading 100 milliseconds of data for 101 inlines and 201 crosslines. Note the code to interactively display slices from the red volume requires the IPy widgets module. This is not included in the OpendTect Miniconda 3 Python environment. The create method of the Seismic 3D class is used to make a new 3D seismic dataset. The method parameters are the target survey, a dataset name, 3 lists specifying the start, stop, and step for the inline, crossline, and Z extents of the volume, a list of seismic component names that will be stored in the volume, the output storage format, which can either be CBVS or SegWide Direct, a bool flag indicating if the Z-axis is time, and an overwrite flag indicating what should happen if a dataset of the given name already exists. The default is not to do anything. If overwrite is true and the dataset already exists, it will be overwritten. The method returns a new Seismic 3D instance. Best practice is to use the create method in a Python with statement and do any output in the scope of the with. This will ensure the new dataset is closed and the associated temporary object is deleted when it goes out of scope. Otherwise, you would need to do this manually. The newly saved object can then be accessed as a read-only object as shown earlier. The assignment to the volume attribute of the new object triggers the save to disk. The input data must be in a similar form to what is produced by the subvolume read. That is, a tuple of a list of NumPy arrays, one for each component, and a Python dictionary with at least the keys iline, xline, and 2itime or depth depending on the Z domain. The values for these keys are lists with the start, stop, and step for each coordinate. For slices, only saving of inlines is supported at the moment. The demo code shows 2 approaches for saving a set of inlines: a basic for loop, and under the comment, a slice index. The colon is the only acceptable index on the left-hand side of the assignment. It signifies that the metadata of the input should be used to match the input traces to their location in the output. The next example shows trace output. In this case, slice notation is used in the index on the right-hand side of the assignment to select 101 inlines from 200 to 300, but only the 21 cross lines 400, 410, 420 up to 600. Because the assignment index is 2 colons, the coordinate metadata of the input will be used to locate the traces in the output. In 7.03, the assignment index for traces can also be either a trace number, an inline-crossline pair, or a trace number slice. This flexibility potentially allows input traces to be saved in new locations. This is now considered to be undesirable. In the next release, the only acceptable assignment index for the volume, iline, and trace attributes will be a lone colon. No remapping of locations will be allowed. Finally, the delete method can be used to remove seismic datasets from a project. Here, the volumes created earlier in the demo are removed. Also, we can use the names method to just check that that's happened. Let's quickly look at the well data class. Functions from the Common API are present to get information about some or all of the well objects in the project. Shown here is the names function that returns a list of wells in the project, and the features function that returns a GeoJSON representation for the wells that can be used in a web map. Working with wells requires creating an instance of the well object using the constructor that takes a survey instance and the name of the target well. This instance can be used to call various methods to get information for the well. This includes a summary of logs, markers, and the well track. Depending on the function called, the information is returned as either a simple dictionary or as a pandas data frame. Likewise, there is a logs and logs data frame method to get a regularly sampled set of log data for a selection of logs. The sampling can either be by linear interpolation or upscaling. Upscaling is just averaging over the sample interval. The logs data frame method in 7.03 stores the log unit of measure as a multi-index in the output data frame. This complicates accessing the data and will be removed in the next release. The put log method can be used to save a log back into the project. Note that the last parameter of the function is a Boolean flag named override. It is set to true, indicating any log of the same name will be replaced. Here I just double the gamma ray log and save it under a new name. I then use the pandas matplotlib integration to display the original log and the new log. Finally, the delete logs method removes logs from the well. The success of the operation here is confirmed by using the log names property before and after the deletion. Our plans for the future of odbind include: split the odbind module and plugin into a separate open source GitHub repository. This will make it possible to build the plugin without the burden of building all of OpendTect from source. This should make it easier for developers outside of DGB to contribute to odbind's development. Implementing create, save, and delete for all current data classes. Making X-array datasets and pandas data frames the default output containers. We also want to refine the data access APIs to be more consistent across classes. Want to ensure the X-array coordinates and dimension names are consistent across all data classes. And we want to expand the coverage to a greater range of OpendTect data types. We hope that those with an interest in using Python with OpendTect will fork the new odbind repository and help make the code better for all. Thank you for your listening.